Hello everyone. Today what I'm going to be doing is going over a solution to a previous problem that I did in more detail. I had a viewer submit a problem recently, and the solution that I came up with wasn't the same as the solution that was intended by the original submitter. And it was mentioned in a comment that they didn't quite fully understand exactly what my thought process or what my solution was. So I thought that what I would do is clarify that here and make the argument a little bit more rigorous. So I'll start by reading out the problem. We're given a polynomial, Pn. The coefficients of the polynomial are the same as the Fibonacci sequence. So Pn is equal to 1 plus x plus 2x squared plus 3x cubed plus 5x to the 4, and so on. And the question is, for which value of n does Pn of x equals 0 have an integer solution? So the intended solution by the viewer that submitted this problem, and in fact it was brought up in comments on the original video by other viewers, was to use what's called the rational root theorem. This is a result from algebra that talks about polynomials with integer coefficients and any roots that are rational and relationships between the rational root and the coefficients of the polynomial. This did not come to mind at all to me when I was solving this problem, and the solution that I came up with is more of an analytical approach. So I'll put a link in the description to the details of the rational root theorem. This question is a lot easier if you use the rational root theorem than my approach. But I thought it would be nice to outline what I'd done here anyway. Okay, so the first thing I'm going to do is I'm going to rewrite this polynomial in the opposite order, so like in terms of descending powers of x, because I want to group terms in a particular way. Okay, so I've written the polynomial so that the powers of x are now descending. And what I'm going to do is I'm going to consider pairs of adjacent terms like this. And depending on whether n is even or odd will dictate whether I have to group these two terms together, and then the constant term, which is just equal to 1, is sort of on its own, or if both of these terms at the end can get paired together. So I'll break this up into two cases, whether n is even or n is odd. So I've made it clear now that I'm grouping terms in pairs, and when n is even, the total number of terms in the polynomial is odd. So we have one leftover term here, which is the first term of the Fibonacci sequence, which is 1. So another thing that we have to recognize is any real root of this polynomial has to be negative. If you evaluate the polynomial at x equals 0, you end up with a positive number, and all of the coefficients on the polynomial are positive. So for all positive values of x, the value of the polynomial will be strictly greater than 0. So any real root has to be negative. And we're also looking for integers. So of course, our only candidates that we care about are going to be -1, -2, -3, and so on. So what I want to do at this point is I want to look at one of the individual terms in this sum. So I'm looking at one of the terms in this sum. I want to evaluate it at some negative integer. So I'm going to let m be an integer which is positive, but then I'm evaluating it at -m. This is what that term is going to look like. We can simplify this a little bit. So the fact that I have an even power here means that -m raised to that power is just going to give us positive m to the power of 2i. But here, the exponent is going to be odd. So -m raised to that power is going to give us a negative sign here times m to the power of 2i minus 1. And if you look at this number is clearly strictly positive. First of all, the Fibonacci coefficients are strictly increasing as soon as the term in the sequence is the second term or higher. Additionally, m is a number which is greater than or equal to 1, and so this number here is greater in magnitude than this number here, well, greater than or equal in magnitude. So the fact that both of these here are greater than or equal to both of these here, and we're taking a subtraction, means that this term is positive. So what does this say? This says that Pn evaluated at negative m is strictly positive for all integers m strictly positive. Okay, so we've immediately ruled out any integer solutions to our original equation when n is even. So now I want to look at, I want to basically repeat the entire argument, but I want to consider when n is odd. Okay, so for odd values of n, the polynomial can be written like this. There is no leftover term now because the total number of terms in the polynomial will be even, so we can group them in pairs like this. And I again want to consider an individual one of the terms in this sum evaluated at any negative integer. So we're going to do the same thing that we did in the case when n was even. We're going to let m be an arbitrary positive integer, and we're just going to sub in negative m to this expression. Now the exponent on the higher term, or the higher degree term, is odd, so we have a negative sign here multiplied by m to the power of the original exponent. This exponent is clearly even, so the negative sign disappears. Now we have to be a little bit careful because we actually have to consider values of m and of I. So once again, this Fibonacci term is strictly greater than this Fibonacci term, except when I is equal to 0. When I is equal to 0, both of these terms are equal to 1. It's the first two terms in the Fibonacci sequence. Additionally, this term here is strictly greater than this, except when m is equal to 1. Okay, so this term, if you put those statements together, this is again strictly less than 0 for all I not equal to 0 and all m not equal to 1. Okay, so the only case where this term is equal to 0 is when both I is equal to 0 and m is equal to 1. So if you put together these two statements for the even value of n and for the odd value of n, we see that there's only going to be one integer root. And that one integer root happens to be negative 1. So I hope this clarifies the thought process or the solution that I had from previously. I had no idea that this is the approach that I was going to take on this question when I began it. If you watch the original video, you'll see that I tried a couple other different things, and then I just sort of stumbled upon this idea, but I didn't quite fully expand upon it, so it may have not been completely clear exactly that this followed. If I have any additional comments about this, I'll put them in the description. Thanks for watching.